Okay, folks, so we are in our last section of Module 8, and we're going to talk about types of errors. Remember that when we developed the confidence interval was based on doing many samples and calculating many confidence intervals. But in the end, we only take one sample and calculate one confidence interval, so we are either right or we are wrong. The same thing happens with hypothesis testing. In real life, we never know if we got a bad sample that made us make a bad decision in a hypothesis test. There's a probability of making a bad decision associated with any type of hypothesis test. These bad decisions are called errors, and they are not human mistakes. Rejecting the null hypothesis when it's actually true is called a type 1 error. And we typically use Roman numerals, but I don't care if you use regular numbers. The probability of making this type of error is alpha. So the probability of type 1 error is alpha, and we control this number. That's that 5% our level of significance, or 10% or 1%. Failing to reject the null when it's actually false is called type 2 error. The probability of making this type of error is beta, and we can calculate that, but we won't do that in this class. It's a little bit beyond the scope of this class. And then the power of the test against a specific alternative hypothesis is the probability that the test will reject the null at a chosen significance level, alpha, when the specified alternative value of the parameter is true. And the power of the test is 1 minus beta. And what we're really doing here is saying the power of the test is the probability or the chance of rejecting Ho when we should. So it's a correct decision. Decreasing type 1 error increases type 2 error and vice versa. To control both type 1 and type 2 error, we have to increase sample size. But big increases in sample size only make small decreases in the probabilities of the errors. So alpha, beta, and sample size n are all related to each other. And alpha and beta are inversely related. So if one goes up, the other goes down. And we have to make huge jumps in n, or sample size, to get both alpha and beta to go down. So because of that, instead, we try to control the error that's most dangerous. For example, if type 1 error might result in human death, we would want that error to be very small and would tolerate a larger type 2 error that might only result in a higher cost or wasted product. A good example of this is false positives and false negatives in cancer screenings. So for example, if someone goes to get a mammogram to test for breast cancer, and then they're called back for additional testing, but they didn't have cancer, that's called a false negative. A false negative costs money, it costs time, but it doesn't miss cancer. If we have sorry, that was a false positive. If you have a false positive, it makes you come back. And extra money, extra time. If, however, you have a false negative, what happens there is you miss the cancer and the person goes another year without getting a mammogram, and that cancer grows. So that false negative is really dangerous. And so because of that, mammograms have about a 30 to 40% false positive rate, so that people get called back more often than they need to be, so that the false negative rate and the chance of catching cancer is much better. So we try to control things in hypothesis tests the same way, and it'll all just depend on that particular scenario. But we won't be controlling those errors in this class. All you need to know is that there are errors and what type of error is possible. So let's go back to our seed example. The agricultural seed company claims that less than 40% of seed species is genetically modified. And so we did this test. Our alternative was that P was less than 40%. We calculated a p-value of 0.0331, We rejected the null, and we concluded that there was evidence to show that the true proportion was less than 40%, so it supported the company's claim. If we reject the null hypothesis, then we are in this section of the error table. So in the error table, we either made the decision to fail to reject the null. If that happens and the null is true, we've made a correct decision. The chance of that happening is 1 minus alpha. If we failed to reject the null and the null is false, we have made a type 2 error and the chance of that happening is beta. If, however, we rejected Ho, which is what happened in our example, and the null hypothesis is true, we made a type 1 error. If we reject the null when the null is really false, we made a correct decision. So for our scenario, we rejected the null hypothesis and were asked, what type of error is possible? Well, once you reject the null, you're on this bottom row of the table. The possible error is alpha, is type 1, and the chance of that error is alpha. So type 1 error is possible, but please know it is unlikely. So it's unlikely we got a bad sample. More than likely, we made the correct decision. If we had used an alpha of 0.01 though, so our level of significance alpha was 0.01, what decision and conclusion would we have made? Well, our p-value, recall, was 0.0331, and I'm just pulling that. I had put it on the previous page for us. And we had an alpha of 0.01, well, 0.0331 is greater than that. And so we would fail to reject Ho. But for our example, we rejected Ho. And so does this change the decision from before? Yes. The level of alpha we chose or choose matters when that p-value is in that range. And so what happens is it changes our decision, it changes our conclusion, and it would change the type of error possible also. The type of error is now type 2 would be possible here. So it's really important to choose our alpha level before we ever start the test, or to know that there's a level of significance cutoff level that we decide on in our field. And if you don't want to decide on a level of alpha and you don't want to actually decide that, you just report the p-value. And you make some arbitrary decision, but someone else could make a different one if they wanted to. All right, and then we did the next example, which was the colorblind example. We had a sample of 750 people, 38 were colorblind. We were testing to see if the proportion was more than 4.5%. We did the test. We found a p-value of 0.2270. We failed to reject the null, and we concluded that there was not evidence that the p proportion was more than 4.5%. So our type of error now is associated with the fact that we failed to reject the null. If you fail to reject the null, you're on this top portion of the error chart. And so if we fail to reject the null, we either make a correct decision, which is almost certainly what we did, or a type 2 error is possible. So type 2 error is possible, but unlikely. All right, you guys, that's it for that section. I do recommend doing the practice. Bye, everybody.